This is problem number 2 from chapter 11. It says here 6-sided die is rolled 120 times. We want to fill the expected frequency column, then conduct a hypothesis test to determine if the die is fair. Well, if this is a fair die, then each of these would have probability of 1/6. And so if this has a probability of 1/6 each, we should expect the outcome to be generally the same. And out of 120 rolls, 120 and 6 rolls or 6 possible outcomes, all equally likely, then we should get our expected values to be about 20. So this particular hypothesis test that we're going to do is called a goodness of fit test to see if the data that we collected would fit the actual model that we're expecting. And if we look at this, it looks like there's a number 5 that gets 30 and number 2 that gets 29. Everything else is below 20. But how far off is 5 and 2 from this model is the question that we're going to try to answer. So our null hypothesis, whenever we do a hypothesis test, we should be ready to set up a null and alternative hypothesis. And mathematically, the null hypothesis would be commenting on the probability of each of these outcomes. So these are the outcomes. This, by the way, are observed frequencies, and these are expected frequencies to prepare us for our test statistic. But the outcomes here are based on the probabilities. So we can say that the probability of rolling a 1 is 1/6, and the probability of rolling a 2 is also 1/6. And we can just go on and say the probability of rolling each of these things is equal to 1/6. So we can say that this is all our null hypothesis stated in mathematical form. But I think they want us to write it in words, and writing this in words would make a little bit more sense to us. So the null hypothesis in this case is that the rolls of the dice will fit the expected probability. One way to put it. Let's not say will, let's say roll of the die fits the expected probability. And then the alternative hypothesis is the complete opposite, so we can say that this does not fit. And so that's why it's a goodness of fit test, because it tests how well our data will fit the expected values. Okay, now that we've got that, we should also mention our distribution that we're using. This is a chi-square distribution. I know it looks like an X, but chi is a Greek letter. Chi-square distribution. And our distribution that we're using for this particular hypothesis test would be a distribution on X, and it's going to be a chi-square distribution, and our degrees of freedom is going to be the number of categories minus 1. We've had a bunch of DFs in the past, well, not a bunch, but our t distribution usually is n minus 1, and here our n, the number of trials that we had, is 120, but this time our degrees of freedom is based on the number of categories. So in our particular problem, our degrees of freedom would be 5, and so we would denote our distribution by chi-square sub 5. Now let's find the test statistic. The test statistic is going to be based on this formula, and one way to do that on the graphing calculator, well, actually one way to do that is to create a couple of columns here and then figure out our values, but I'll tell you how to do it using the TI-83 and 84. The first step is to get these observed and expected frequency values on a list. So I'm going to go to Stat and just edit, so just press enter and make sure that your values are inputted correctly in your L1 and L2. So using our calculator, I put these observed values in L1 and I put my expected values in L2. And so using the calculator, let's go back to the home screen just to be safe here. So second function and quit. I've already inputted my stuff in L1 and L2. I want the sum of the O minus E squared divided by E. So if we just replace the O with L1 and the E with L2, and then find an appropriate symbol for the sum, or calculator command, then we'll be all set. So here we go. Second function and stat. We have, we're using our list operations here. We go to OPS, one more, math, and then the fifth one down is sum. So now that's the sum. We have an open parentheses. For the numerator, we need another open parentheses, and my observed values are in L1. So second function and the number 1 would give me my L1. Second function and number 2 would give me my L2. So L1 minus L2, close the parentheses, and let's square that. And then now divide by E, which is L2, second function, number 2. And here is our test statistic. So our test statistic comes from a chi-square distribution, so we should label that appropriately. Chi-square is equal to 13.6. Now the next step we need is to figure out what our p-value will be. So by the way, these are always right-tailed tests. Our chi-square distribution starts at 0 and goes like this, and it's skewed to the right. Our test statistic is given here at 13.6, and so we're looking for this probability value, shaded region, and we can find this value by going into the calculator's distribution function. So we've been here before, second function distribution. We've been here before when we were looking at the binomial distribution as a normal distribution. So somewhere down in your calculator you're going to see a chi-square. CDF is what we want, the cumulative. And so on the calculator, the chi-square CDF looks for a low, a high, and because this changes with respect to the degrees of freedom, it needs that as an argument as well. Alright, so I'll select number 8. Oops, let's try that again. Let's select number 8, so that's chi-square CDF. Our low is 13.6. Our high, now remember, if it goes on forever like in this case, we'll label it as 1, and then the scientific notation E, 99 zeros, that's a very large number. And then don't forget your degrees of freedom, which in this case is 5. And let's figure out what that is. So we got a p-value of 0.01836. So a good alpha to compare this to is the alpha is 0.05. So if we assume the significance level is 0.05 and compare this p-value, our p-value is less than alpha. So we can say that we reject the null hypothesis in this case. So we're rejecting the null hypothesis. What was the null hypothesis? The null hypothesis was this was a good fit. So it doesn't look like it's a good fit because we rejected the null hypothesis. And so if it doesn't look like it's a good fit, then it doesn't seem fair. So the die does not seem like it's a fair die. And I think that's about all we can say about this particular problem. And we were able to reject the null hypothesis. Now, for some of you with a TI-84 Silver Edition or something later, sooner, more recent, I mean, there is a nice little program that you can look at to calculate this test instead of doing what we did with a L1 and L2 list business. Let me just go through the calculator motions, and we'll see that we should be getting the same test statistic and the same p-value. So let's go to Stat, Tests, and I'm going to scroll up to see the bottom part over here, and there's a chi-square GOF test. GOF stands for goodness of fit. We have our reserve values in L1, our expected values in L2 already, and our degrees of freedom in this case is 5. So let's put 5 there. And we can ask it to calculate. We can also ask it to draw. We might as well ask it to draw because we'll see the graph. We should see the test statistic and a p-value. And here's a drawing of the chi-square distribution. I notice it's skewed to the right. A really small area over here. Our test statistic is 13.6. Our p-value is 0.0184. So we get the same results a lot quicker. I thought I'd do this using the L1 and L2 list because there are some calculators that don't have this special feature. And if you don't have this special feature, then we could do it the original way that I did it. Alright, so I hope this helps with the goodness of fit homework.